Hello all and welcome to this course on computer organization. So this is the first lecture and I would like to take you through the course organization before I get into the details of the actual course. So here is the course structure. The computer organization that we are going to talk about is going to be divided into two parts. Okay, first we are going to understand uh, how a C program is translated to assembly language. What is assembly language? Assembly language is a sort of uh, almost human readable mnemonic, as you will see a little later, which will, the human can understand what it actually means by just reading that instruction, but it is a one-to-one mapping to a binary instruction that a computer can easily interpret, right? So most of us are already familiar with a C program, right? And in fact, that's the reason what is shown in yellow here in the box is actually a prerequisite. So all of you have already done C programming and therefore you are familiar with writing C programs. The focus in this part of the course is actually to take a C program down to the assembly instruction and very precisely understand how a C program executes on a microprocessor, right? So when you compile an executable and you go run that executable, what exactly happens, at a nuts and bolts level in the microprocessor is what we are going to look at in this part of the course. So here we will introduce you to assembly language programming, the concept of assembly language, and all the necessary components at an abstract level of a computer, right? We will not get into how to implement them, but we will at least know what the components are and what those typical how those typical components are used in order to execute a C program. The second part of the course is, typically somewhere after 6 weeks, right, is when we will shift to implementing the C program. Okay, or sorry, not implementing the C program, implementing the microprocessor itself in hardware, right? And for this, the prerequisites is you need to know digital systems very well. So you should know how to design a combinational circuit. You should know how to design a sequential circuit, how to use them, how to design a finite state machine, and all of these details will actually come into the picture here for you to be able to implement a microprocessor. So there are various flavors of computer organization. There is a computer science view to this which talks about the architecture, and sometimes the course could also be called computer architecture. There could be some overlap, but I'd like to reiterate in this particular version of the course, because it's an electrical engineering computer organization course, we will be focusing on certain electrical engineering aspects of computer organization, namely how fast can a processor actually work, what is the maximum clock frequency at which it will run, and how does adding like a new instruction to the microprocessor affect the delay and so on. So I would say that is going to be a slightly different electrical engineering viewpoint of this computer organization course, and that will sort of differentiate this course offering from other computer architecture courses that might be available from many other experts. So for now we are going to only focus on the first part of the course, which is taking a C program down to assembly. But before that, let us look at what kind of computers are available with us today, right? Because we live in a very, very interesting era, because today you have something called chat GPT, right, or Claude or whatever, which is able to talk to a human being almost like another human being, right? You are able to ask it all sorts of questions in natural languages. There the computer is able to process that question, it's able to respond to you with very relevant responses and stuff like that. Now all of these are possible because of the advancements in compute technology, right? And that is largely thanks to the Moore's law and scaling of transistors at some level. So computers typically today can be classified as desktops, servers, and you also have mobile processors, right? So each of these fundamentally will be very similar in its operation, but they are optimized for different kinds of performance parameters. For example, a mobile processor, because it is running off a battery which has finite energy, it is not going to be wise to sort of do some very energy hungry operations on this, right? So that's why you would have heard this concept of a mobile phone always talking to some sort of a cloud server or a server or something like that, right? Because essentially a mobile cannot be wasting energy performing very compute intensive operations. So it can do some rudimentary operations, not that the processor is not powerful enough. In fact, today's mobile processors are more powerful than yesteryear desktop processors, okay, way more powerful. So of course they are all powerful, but in order to perform those computations you need a lot of energy, and if you do perform those computations you're going to drain your battery before you can do this, right? So that's the reason you don't do too much on a mobile processor. So the mobile processor will be optimized for energy consumption, right? With some, of course, with a very reasonable performance, okay? Desktop, I would argue, is sort of, remember, a desktop is plugged into a plug point, right? Of course, laptops are also available. I would say laptops and desktops I will use interchangeably. But remember that laptops are also much bigger than mobiles, and for this reason the battery will be much larger, and therefore the laptops, for all practical purposes, you can assume has a large amount of energy available for computation. So therefore the desktop or laptop processor will be optimized to actually give you much better performance than the mobile phone processors, but of course at the expense of a lot more energy consumption, right? The servers, on the other hand, are the high-end processors. I mean, these cannot be run off batteries and all that. You have to keep them connected to a power source always. What does connecting to a power source mean? It means that you have infinite energy, and therefore you don't, these servers are not going to be optimized for energy, but they may still be optimized for power. Power and energy are different, right? Power is the rate at which energy is dissipated. If you dissipate too much of energy very quickly, the heat generated will be much higher. Taking the heat out is a problem, and therefore you have to make it a reasonably low power processor, but the energy consumption could be quite high out there, right? But in any case, the fundamental concepts of the microprocessor, right, that is residing in these systems, right, be it mobile or desktop or server, they are going to be very similar in nature, right? Of course, a server, for example, might have like a 24 core machine, right, or a 60 core machine, 80 core machine. Mobile might have maximum maybe 4 cores, right? Desktop maybe they can have about 32 cores today, or 24 cores, or something like that, right? So it could be, the number of cores could be different, but each of these processors essentially do something very similar in nature. So let us look at, how the microprocessors have actually evolved over various, over time. And this is basically the Intel desktop or the mobile processors. And basically what you see, right, on the, there are 3 graphs here, right? One is on the top graph, we are showing you the number of cores, the number of threads, and the cache size. So this started, on the x-axis, we are talking about the 45 nanometer technology, the i7, the 32 nanometer i7, 22 nanometer, all the way to the i9s, which is in 7 nanometer, right? And the year is marked below. So it starts from 2009 all the way to 2024. So if you look at the top graph, what it is basically saying, you just focus on the red line, right? It's basically the number of cores, right? How many cores? So mostly for a long time, people were trying to optimize the performance of a processor with just a single core, right? Now, how do you optimize the performance? You make the clock frequency faster and faster, better and better and better. And this was achieved because of the scaling of the transistor, right? Moore's law, essentially, right? But beyond the point, people realized that, just making a processor was not fast, it was not good enough, and therefore it was better to sort of keep the clock frequency at some reasonable rate and add more cores to it, right? So that's what you see, where the red line from 1, right, from 2017 i7 14 nanometer, it went up to 2 cores, 3 cores, and then many more cores, sort of jumped up significantly to about 20 cores, and maybe a little more than 20 cores in 2024, right? So the number of threads, right, or the number of threads also saw a similar growth over the same time. Now the cache size is very important because you'll see in this course a little later that how you use the cache is also very important for the performance of the processor, because there are various kinds of memory, right? You have the caches, you have the main memory which is sitting outside the processor, but that takes a long time to access data. So you have cache memories which are sitting in between your microprocessor and the main memory, and this basically grows. So the size of this cache memory, because the caches are faster to access, but you cannot make them indefinitely large, right? The size of this cache has been growing significantly to close to about 30 MB or so, right, on chip, right? That is what has happened on the desktop and mobile processors. On the second graph, you see the maximum clock frequency. Of course, the clock frequency has also been growing from 2009 to 2024. Likewise, the maximum memory size is also going all the way to about 200 GB nearly, right, in 2024. It started with a couple of, tens of GBs, right, early in 2009. Okay. Similarly, memory bandwidth is also growing over time, right, because it's not just about storing a large amount of data in memory. You must be able to access that data quite fast. So the memory bandwidth is, by the way, not growing significantly as compared to the other, parameters that we saw. So therefore, it is sort of, if you look at this, it is sort of lagging here, right? So the idea of computer organization is to sort of optimize the performance of your whole core or the computer in order to maximize, the throughput at which your system can operate based on all these constraints around you. How much memory you can have, how much cache you can have, what is the memory bandwidth, how fast you can access the main memory, and so on, right? That's the general philosophy of computer organization. Now, interestingly, the servers, right? So on one side, from 2009 to 2024, you saw the mobile and desktop processors take a, follow a certain trend in their evolution. It turns out that the servers also had a very, very similar evolution. In fact, just that the base size itself would be very, very different. So if you look at the number of transistors, right, which is basically shown in red, it goes all the way up to something like 10 billion or something like that, 10 billion transistors. And the blue line is the number of cores, and that's going all the way to about maybe 50 to 60 cores, right, in the P10 processor, which was 2020. So number of transactions, right? So if you look at it, number of transistors in millions per mm square, which is basically the density, right? What is it's telling you is the number of transistors is actually going up, right? In billions, it's gone from a couple of 100 million to a few billion transistors now. However, you will also notice that the chips have become bigger, right? So how do you actually say that, one technology can accommodate 11 billion transistors, another technology accommodated 8 billion transistors? I cannot say anything about these two because I do not know in how much area these two were accommodated. That's why you look at the density, which is the number of transistors in millions per mm square, and that's in green, right? And you see that it goes from P6, which is 2007, the Power series in 2007, say P6 processor, all the way to P10, it has gone up to near about 10 million transistors per mm square, right? And the L3 cache is basically another interesting concept, which is basically the size of your more or less it's quite a large cache, and it was the last level cache for most servers, but now you also have an L4 cache, right? So if you look at that, that has also grown steadily over time. Okay, so in some sense, this is what I meant by the desktop and mobile processor are similar in nature to the server, right? You just throw many more cores, a lot more power at the server, you optimize it for different parameters, but in the heart of hearts, all these three processors are going to be very similar in nature, right? So this is actually the picture of an IBM Power9 processor, right, which is shown here. This processor was, this was published in 2017, and it has 6 quadrants, quad 0 to quad 5. Each of those quadrants, when you blow it up, it has 4 cores, core 0, core 1, core 2, core 3. What you see as L2 and L3 are basically the shared level 2 and level 3 caches. So L2 is a smaller memory compared to L3. You just look at the area of L2 and L3, it will tell you the size of that memory, right? There is an L1 cache which is inside each of these cores. That's not explicitly shown in this diagram, right? So state of the art servers, how do they look? The technology in which the P9 was built is 14 nanometer FinFET SOI technology. P10 was built in 7 nanometer bulk technology. Let's not worry about those terminologies here. Number of cores in P9 was 24. Number of cores in P10 jumped up to 60. You have almost a 2x increase, right, in number of cores. Area was 695 mm square. That came down to 602 mm square, right? But number of transistors in 14 nanometer technology was 8 billion transistors. Number of transistors in 7 nanometer technology, right, was 18 billion transistors. So even though the area was about 600 mm square, right, you have packed 18 billion transistors now in the same area compared to, in fact, in a smaller area compared to the 8 billion transistors in 14 nanometer technology. Okay. Number of metal levels, again, if you look at it, metal, let's not get into this. So these are how you actually connect one node to another, right, in a IC, in a chip, right? So these are done through metal levels. And what are metal levels? Basically, these are like, so if I want to connect point A to point B, right, and I also want to connect point C to point D, which is crossing each other like this, right? Obviously, I cannot do it at the same plane because these two wires will short each other. So what you do is you do it like a flyover. One metal runs like this, the other metal runs above it like this or like this, it doesn't matter, but they are all at a different level in the Z axis, right? And that's how you are able to connect these 18 billion transistors to each other. Otherwise, just connecting them in 2 dimensions is impossible, right? So that's the fundamental technology which has enabled us to pack so many transistors and build a microprocessor out of it.